Welcome to this class. And in the last class, I will just briefly gone through the application of APT and transmission Kikuchi on the grain boundaries and how the structural and chemical information is used to identify the root cause of the mechanical properties or the corrosion properties. Now we will go further into the details of the defects, which are very important during the creep deformation of high temperature alloys. Coming back to the application of atom probe tomography and electron microscopy. So now I will briefly go through the electron channeling contrast imaging of the defects from the bulk samples, site-specific specimen preparations, and using conventional and high resolution TM and use of atom probe tomography to get the segregation effects. So here I will give you briefly example of a super alloy. So this is a turbine engine, and this turbine engine usually these are main uh, uh, thrust provider for the aircrafts and the aeroplanes, and it has a certain the cross section consists of an air inlet, compression, combustion, and exhaust. The air inlet, the air uh, gets in, it compressed with a high pressure, and when it reaches to the combustion zone, there will be ignition of the fuel, and due to which the combination of air and the fuel, what will happen, the temperature rises to up to 1500 degrees Celsius, and due to which there will be a large amount of heat and the pressure at the at the components in the combustion zone and the exhaust zone. And usually the materials which are used for the components of this combustion zone are called nickel-based superalloys, and they are used in the form of single crystals. So usually they avoid using the grain boundaries because grain boundaries are the major source for the creep deformation at high temperatures. Okay, so these are special class of materials which are called superalloys. They break down after certain service life, and this breakdown happens due to the certain amount of stress and strain accumulation and the defects, correct? And if these defects are increased from a certain critical value, then the failure takes place. So to understand these defects, it is very crucial to understand the nature of these defects so that we can control over the service life of these superalloys, because during creep deformation these defects are present throughout the microstructure. Okay, so typically superalloy microstructure, there is a cuboidal gamma prime phase. The bright lines corresponds to the gamma phase, and these gamma prime precipitates are the L12 ordered precipitates. If you take a composition profile across the gamma gamma prime, you can see at the gamma phase there is an enrichment of cobalt, chromium, rhenium, and tungsten, and partitioning. And while in the gamma prime there is a enrichment of aluminum, titanium, tantalum, and niobium. This shows that these green color aluminum, titanium, tantalum, niobium are the gamma prime stabilizers, correct? And as cobalt, chromium, rhenium, tungsten are the gamma stabilizers, okay, across the interface. Fine. So you have a compositional partitioning between the two phases, and the volume fraction of these gamma prime is usually kept at 65 to 75%. Okay, to get the both high temperature and the room temperature strengthening properties. Now we will go to the little bit basics related to the defects which are present in these structures. Now this is an FCC gamma disordered unit cell. Okay, here all the elements are in the solid solution, and they occupy both 0, 0, 0 positions and also half of 0 positions. But in the L12 gamma prime, this is a ordered FCC based L12 structure. 0, 0 positions are occupied by one set of atoms, and half of 0 positions are occupied by another set of atoms. Usually aluminum, titanium, niobium, tantalum occupies the 0, 0, 0 positions, while cobalt, iron, or cobalt, nickel, chromium occupies the FCC half of 0 positions. Fine. So in any unit cell, there is a vector which is called Burgess vector, and for FCC, the perfect Burgess dislocation is A by 2 1 1 bar 0. This is defined as the smallest vector from the same lattice point to another lattice point, which these can shear. Okay, this is the smallest vector where the one atom can transport it to the another atom. This is called half 1 bar 1 bar 0. But in the case of ordered lattice, this is not the smallest vector. The smallest vector is from this position to the another lattice position of 0, 0, 0. That is, so it means that 1, 1 bar 0 is the smallest lattice vector for the L12 gamma prime. However, you can see that the A by 2 1, 1 bar 0 from the red to this golden color atom half of 0 position, this vector is called super partial dislocation. So the perfect dislocation in FCC gamma is a super partial dislocation in the ordered gamma prime unit cell. Due to this ordered nature, it produces different types of defects on the triple one plane. So this is your top view of the triple one plane, and you can see that the black corresponds to the black corresponds to A, and the white color, the uncolored corresponds to the B, and different size of these circles corresponds to the position A, B, and C. Okay, and these are the different directions projected on the triple one plane, and based on the direction of movement of the dislocation, you will get different types of stacking faults or the planar faults. Okay, so if you move half 1 bar 0 1 position, okay, you can get the anti-phase boundaries, and these are have a very high energy of 100 millijoule per meter square, because they usually nearest neighbor violate. So means the nickel aluminum bonds are converted to the nickel nickel bonds or the aluminum aluminum bonds. How and if the dislocation shears by 2 bar 1 1 dislocation then these may form intrinsic or the extrinsic stacking faults. Here there is no nearest neighbor violation, so they have a very low energy. So the propensity of forming these stacking faults will be very high. If they shear by A by 6 1 bar 1 bar 2, this is a small vector, then it violates the nearest neighbor violation similar to the antiphase boundaries and has a higher energy, which is around 250 millijoule per meter square. So depending upon the shearing direction, you will get different types of faults. And these shearing directions are governed by the temperature and the stress conditions of that particular alloy. With this example, I will give you a multi-component cobalt nickel based superalloy which have been heat treated by these steps and followed by water quenching. And this shows a very uniform distribution of gamma prime precipitates in the gamma matrix space. However, if you see the after the tensile creep at 850 degrees Celsius with 400 MPa of stress, you can see that these gamma prime cuboidal precipitates converted to a rafted structure. So the gamma prime precipitate in the sample gets rafted along a particular direction. So these are the positive misfit alloys where the gamma prime has a positive lattice misfit. So if your loading direction is in this direction, your rafting also takes place in the same direction. Okay, and this is a controlled electron channeling contrast image of the deformed sample, and these gamma prime precipitates are rafted. If you see in these gamma prime precipitates, you can see that there is an appearance of bright linear features. These bright linear features are nothing but the planar faults in the sample. If you magnify the particular region, you can see that these bright features are corresponds to a different types of variants at different triple one planes. So this is a ECCI image. You can see the gamma matrix is dark, gamma prime is relatively brighter, but these features are much brighter than the gamma prime. So these are in the channeling condition. So you have made the 002 bar diffracted beam is channeled through the sample, and due to the presence of defects, it got back diffracted and gets the higher backscattered electrons and from those regions. And those electrons are used for the imaging purpose so that you will get a bright intensity areas at these locations. Now you have an orientation of this particular grain, so you can map out these crystallographic planes by the stereographic projection. If you see, there are four variants of stacking faults: A, B, C, and D. And these A and D are actually uh, uh, showing the bright dark contrast, and which is exactly similar what we see of the dark contrast of the stacking fault in a electron microscope, in a transmission electron microscope. Okay, so with the stereoific projection, you can actually calculate the angles. Like for A and D, these are 36-degree and 38-degree with the sample surface plane. Okay, so these are at the angle which are cutting to the sample. That's why you see a bright dark contrast for A and D. However, the B and C are nearly edge on. You don't see that type of contrast. These are nearly around 80 to 81 degrees from the sample surface. Okay, so appearance of these straight lines or bright areas inside the gamma prime precipitates are the characteristic of the stacking faults. Now you have identified these stacking faults. As you know, in the ECCI, we can also do the G.R analysis invisibility criteria, similar to what we do in the transmission electron microscope. So here the displacement vector is R, which is plus minus 1 by 3, 112. Usually this displacement vector is corresponds to the planar faults. Okay. Now you know the stereoific projection of that particular plane. Actually, you can do the G.R analysis at different vectors by ECCI. So as I explained you that the Z and the X, you can actually get the X and Z values where you can tilt, you can reorient your Kikuchi pattern such that your G vectors are in the Bragg's condition. So in 1 bar 1 1 condition, you can see that the B is invisible. In 1 bar 1 1 bar condition, you can see that C is invisible. In 2 bar 2 0 condition, you can see that both A and D are invisible. Right. So this is exactly same in TM what we can do the G.R analysis. Now we have identified the location. So what we do is we prepare a needle specimen from this particular region where we can cover the C type of stacking fault. We made that needle specimen by in-plane lift out. You can see that this is the bright field image of that atom probe needle. You can see that most of the electrons are transmitted across the sample. Okay, so this is the bright field image and it is near to the 110 direction. However, due to the presence of the stacking fault, you can see that, or due to the presence of stacking fault, these electrons gets diffracted. Okay, and due to which you will see a dark contrast, and these dark contrast linear features corresponds to the stacking faults. Now this is your this is in the bright field mode in the TM. Now the same analysis can be performed, the G.R analysis in TM also, and you can see that in the condition of 1 bar 1 bar 1 bar, you can see that the both the faults gets invisible. It means that if you compare with the bulk analysis, this particular fault corresponds to the C variant of the stacking fault. And you can claim that at which 111 plane it is localized or it is present. Okay, so you can actually both TEM and atom probe can be used to identify the crystallographic nature of these faults. Now you have a needle specimen with the stacking fault. You can go to the high resolution microscope and you can see this is a Hadoff contrast image. As I told you, this is a high angle annular dark field image where the bright where the areas which are brighter corresponds to high Z elements. Okay, it means that the electron beam is scattered at more angle on those areas. If you magnify these regions, you can see these are the atomic columns which are taken along 110 of the cubic direction. And you can easily see that the fault plane, at the fault plane, you can see that there is an increased intensity which corresponds to the more scattering by larger scattering angle. And that's why you will get a large signal in the dark field, angle annular dark field detector. Okay, and it shows that it might segregate the heavy elements. So there is a hint for that. If you take the structure of these stacking fault, you can see that these are the atomic columns. And at this region, you can see there is a change in the sequence of the atomic structure. So if you map the ACB, you can see there is a missing A plane at this location. And this missing A plane shows that this is an intrinsic fault and it is in the L12 unit cell. That's why these are called superlattice intrinsic stacking fault, which is SISF. And as the structure of SISF, these are called DO19 structure, which is a HCP based structure and are coherent with the L12 surrounding unit cell. If you take the intensity profile across this structure, you can see that the intensity increases. It means that it might possible that the heavy elements present in the sample get segregated at these stacking faults. Now you have a complete structural analysis of the one particular fault. Okay, this is a schematic to show that the presence of DO19 structure. Now the same tip needle specimen, we did the field evaporation and you can see that the distribution of cobalt atoms. And if you draw a chromium isosurface, you can see there is a linear feature at the same location where there is a presence of stacking fault. Now this linear feature, if you concentrate the region near to the linear feature and plot a two-dimensional composition plot in YZ, in XZ, and also in the YX plane and projected on a cube planes, you can see that there is a continuous depletion of aluminum and which exactly stops at this linear feature. If you visualize, this is nothing but a stacking fault which is exactly stops at the partial defect. So there is a partial dislocation and there is a stacking fault behind the partial dislocation. So this is the first time what we have shown that the chemistry of the stacking fault and the partial defect is different. Okay, so here this linear defect is a partial defect which is a chromium enriched while the stacking fault is aluminum depleted. Now you have a complete picture of three-dimensional composition analysis of this particular one defect. If you do the YZ projection of the chromium atoms, you can see that the chromium atoms are enriched at the quartile atmosphere. It enriched at the partial defect. So these are nothing but the quartile atmospheres. So in textbooks, we must have learned that the solute segregation to the dislocations are called quartile atmospheres. They are responsible for drag effect of those dislocations. If you see the stacking fault plane, you can see there is an aluminum deficiency along the plane. And this aluminum deficiency along the plane, it is nothing but a Suzuki segregation. Okay, and Suzuki segregation corresponds to the stacking fault. Fine. So we have evidence of both quartile atmosphere and Suzuki segregation, and the composition of these features are different, which was not known before. Now, based on the composition profiles, what we propose is the new type of deformation mechanism which is happening here. So here there is an example of a gamma and the gamma prime. Okay, gamma is a disordered lattice, gamma prime is a ordered lattice. These are the triple one planes, and if the dislocations come near to the gamma gamma prime interface, it can actually shear the gamma prime precipitates. This is due to the application of temperature and the stress conditions. Correct? Once these dislocations shear, what will happen? It will develop a quartile atmosphere along the partial defect, which we see as a chromium segregation. If you take the composition profile, you can see that the both chromium and cobalt are segregated while nickel and aluminum are depleted. If the stress is applied further with the time and at high temperature, this partial defect will shear further and it will transform the L12 structure behind to a DO19 SISF structure. Okay, and this DO19 SIF structure is a HCP based ordered structure in the sample. Okay, and this has a certain different composition other than the linear defect. Now, if you take a composition profile across this particular SiSF structure, you can see that there is a depletion of aluminum and enrichment of cobalt and tungsten, while decrease of nickel content. So here there is a tungsten enrichment shows that it usually tries to transform to CO3W, which is having a DO19 structure. Okay, so this is the bright contrast in a Hada image corresponds to the tungsten segregation, which is a heavy element, which is a high Z element as compared to other elements present in the alloy. Interestingly, if you know the three-dimensional composition profile, we took a composition profile along the plane. Okay, and along the plane you can see that at when the partial dislocation where the chromium is enriched, there aluminum is depleted, but the aluminum is enriched just ahead of the partial dislocation, and also there is an increase in the nickel concentration. It shows that the diffusion of solutes also plays a very important role, and what is happening is the applied stress, as per the applied stress, as the resultant applied stress on the 111 plane, these diffusion of solutes are happening in plane. Okay, so with this we the enrichment of aluminum ahead of the partial, we show that the tungsten and cobalt diffuses towards the DO19 phase, where ahead from the adjoining gamma prime L12 unit cell, while aluminum and nickel actually diffuses towards the gamma prime L12 from the DO19 phase. So tungsten and cobalt occupies those positions while aluminum nickel leaves those positions. So this is how we generate a new diffusional mechanism which is operative during the creep deformation of this particular alloy. Here, tungsten is the rate limiting solute of this particular alloy, and these defects are continuous or homogeneous across the sample. So the mechanism of diffusion is happening throughout the cross section of the sample during creep deformation, and that's why that creep rate limiting solute is identified as tungsten in this particular alloy. Okay, so the next example also is on super alloy. It's a cobalt nickel based alloy with aluminum, moly, tantalum, and titanium. These are all directionally solidified, and based on the composition, based on the temperature and the stress conditions, you can see that this alloy can contains different types of defect structures. Fine. So this particular alloy was directionally solidified along 001 direction. This is the cross section collage of optical image where you can see the dendritic structure. If you take the EBSD map, IPM map, you can see that these are all near to orientation of 001. And this is a typical gamma prime microstructure with cuboidal precipitates of gamma prime with a volume fraction of around 72%. This sample was crept at different stress levels and temperature 800, 850 and 950 degrees Celsius. These are the creep curves, and these are the creep curves, and the TM analysis were performed after the creep deformation. Based on the curves, what we plotted is minimum strain rate versus stress. Okay, so here what we do is if you increase the stress levels, you can see that there is a transition in the slope from a lower value to a higher value. For example, at 800, it goes from 3.1 to 6.8. At 850 degrees Celsius, it goes from 2.3 to 7.4, while at 900 degrees Celsius, it goes from 3.2 to the 9.5. Correct? So there is a transition in the slope. This is called a stress exponent, which is N. And with increase in the temperature, you can see that the transition happens at a lower stress levels. Fine. So it means that at different stress exponents and temperatures, there is a distinct creep mechanisms which are occurring. We also calculated the uh, activation energy. So this is the minimum strain rate versus 1 by T temperature. You can see that at higher stress levels, the activation energy is very high, which is around 400 MPa. At lower stress levels, the activation energy is around 200 MPa, 351.8 kilojoule per mole. Okay, so these are the activation energies. Now, what we do is to identify the deformation mechanism, we selected three samples. One is at lower temperature and high stress conditions, at low stress and intermediate temperature, and at high stress and high temperature conditions. First, we will talk about the lower temperature and high stress condition, low, lower temperature and intermediate stress conditions. At these conditions, what you see is that the gamma at the dislocations are not able to shear the gamma prime precipitates. They are actually uh, pinned at the gamma gamma prime interfaces. If you take an atom map from an interface, you can see that there is a this is the gamma phase, this is a gamma frame phase, which is identified by tantalum partitioning, and there is an appearance of a groove. And this particular groove identifies that there is a pinning of dislocations at the interface. If you take a composition profile across this groove, you can see that there is a segregation of moly at the groove. So here, what we get to know is moly solute diffusivity might be the rate limiting for dislocation climb process, and it has a low stress regime. If you go for a low stress, low temperature and high stress conditions, actually you can see that these dislocations can shear the gamma prime precipitates. It means that you are seeing a presence of large amount of extrinsic stacking faults. Again, this is a Hadoop image where you can see that there is a Z contrast. The atomic columns are brighter, mean the intensities are larger with the surrounding, and these are coherently embedded, and these have a locally DO24 structure. If you see the composition profile, EDS profile, you can see that there is an enrichment of moly and cobalt while depletion of nickel and aluminum, change in tantalum and tantalum. Similarly, if you increase the stress levels, you see that large amount of microtwinning in the samples. Usually microtwinning, the extrinsic stacking faults acts as an embryo for the microtwinning process. Okay, so we prepared an atom probe needle specimen, and this is the needle specimen. You can see identify the T1, T2, and T3. Okay, and this particular sample was field evaporated, and field evaporated, you can see this is atomic structure where it is around 17 layer thick twin boundary surrounded by TB1, means twin boundary 1 and twin boundary 2. The same sample was field evaporated, and we are able to capture TB1. We are not able to capture TB2 because the sample got fractured, but you can see that with the isosurface of 7 atom percentage moly isosurface, we can identify this TB1. If you take the composition profile and the two-dimensional projection, you can see there is a aluminum depletion while the moly is enriched at the twin boundary plane. So remember, when the dislocations are not able to shear, the moly is enriched at pinned at the gamma gamma prime interface at the dislocation. Once the stress levels increases, the dislocation shears, and you can see that the moly is also segregated along the twinning plane. Okay, now coming to the high temperature and the high stress conditions. Here we see that large amount of deformation happening by antiphase boundaries. And these antiphase boundaries are curved in nature. It means that they are on the 111 plane. Because of the wrong nearest neighbors, they have a high energy. So they will transform to 100 plane, which are at lower energy. So there is a curvature induced antiphase boundaries. If you see the atom probe map, clearly as per the expected, there is a curvature inside the gamma prime precipitates. You can see that the cobalt isosurface shows that these antiphase boundaries are curved in nature. Means they are actually the transition from the 111 to the 100 plane. Okay, and you can see that it are also associated with the partial defect. If you take the composition profile across the partial defect and also the antiphase boundaries, you can see that in both the regions, the moly is desegregated. Okay, so there is a depletion of moly and enrichment at the antiphase boundaries of gamma prime interfaces. Correct. So with these conditions, with the three conditions, we see that there are three different types of defect structures with the with three different types of atomic structure and also the chemistry. So, and we can conclude that the Molly solute diffusivity plays a very important role and the rate limiting creep deformation. Based on that, schematically, we have shown that at low stress conditions, these dislocations are pinned at the gamma gamma prime interfaces, and the Molly is enriched along that particular dislocations. And at high stress conditions, you can see the diffusion takes place along the when the gamma prime is shared by dislocations, they form antiphase boundaries and also the stacking faults and twinning, and they based on the atomic structure, usually the segregation and desegregation of moly happens along the fault planes. Okay, so here there is another beautiful example where we predicted the mass transport during the creep deformation. You can see this is a grafted gamma gamma prime microstructure, and if you go for higher magnification, you can see there is a large amount of the planar faults which are shearing, which are appear to shearing these rafted gamma prime structures. If you do we prepare a needle specimen, and you can see that at the needle specimen, you can see the appearance of dark regions which corresponds to the gamma pockets. Okay, and near to the gamma pockets, you can see there is also a planar feature which is a gamma prime. Planar feature which corresponds to a stacking fault present in the gamma prime, and this stacking fault, you can see there is a bright Z contrast. It shows that might be the enrichment of a high Z element. The same needle specimen, what we do is that we did the field evaporation and exactly expected these gamma pockets are cobalt enriched while the stacking fault is depleted in the aluminium. If you take the composition profile, we see that the tungsten is enriched along the fault plane while aluminium is depleted. So the dark regions are found to be cobalt chromium rich with respect to the gamma prime and tungsten tantalum rich with respect to the gamma phase. Based on this composition analysis of the gamma pockets, we also introduced the concept of mass transport during creep and how this mass transport leads to the appearance of the rotation of these gamma prime rafted structure along the triple one planes. So assume that these are the triple one shearing planes, and if you apply a compressive stress, you can see that the dislocations will actually shear along these planes. Okay, if you go for higher magnification, you can see that the dislocations can carry the flow mass from this particular region and transport to the B region, from A region to B region. Similarly, the dislocations carry the elemental transport from C position to the D position. After some time, these two regions will merge and there will be a continuous flow of these fault planes across the precipitate. And with time, these will develop as a raft structures along the triple one planes and formation of shear band formation along during the creep deformation. So this is how we identified the mechanism based on the segregation behavior of of these faults that are responsible for the transport of solutes from one side to the another side of the rafted structure. Okay, so with this example, I have shown you the electron channeling contrast imaging use of by FIB. And now what I will do is I will give you some brief examples of site-specific preparation of FIB samples from the FIB, and direct use of atom probe tomography can get the more information related to the microstructure. Okay, so we'll talk about the interface segregation. Here you can see that there is an alloy where the rhenium is added, and here these are not perfect cuboidal shock. shaped precipitates. These are round cornered shaped precipitates. Okay. Now, if you do the atom field evaporation, you can see that the distribution of rhenium atoms and the niobium atoms, rhenium is is partitioned to the gamma phase, while the niobium is partitioned to the gamma prime phase. If you take the composition profile, interestingly, what we see is there is an enrichment of moly and rhenium at the interface. This enrichment actually causes change in the local lattice misfit, and they may cause the lowering of the lattice misfit. If there is a lowering of the lattice misfit, definitely the coarsening resistance will increase. And if you keep this sample at 50 hours and 1000 hours of exposure, the gamma prime microstructure is stable. As otherwise, without rhenium alloy, these gamma prime microstructures phase transform to the equilibrium needle-like specimens or the TCP phases. Okay, so due to the interfacial segregation of rhenium and moly, these microstructure get stabilized even at 900 degrees Celsius up to 1000 hours of exposure. Similarly, in aluminum alloys, we do the novel alloy development. So usually aluminum copper alloys are the major source of aluminum alloys, where the copper forms a theta prime precipitates. These precipitates are room temperature strengthening, but they are very poor in high temperature beyond 200 degrees Celsius. So what we do is we added zirconium, tantalum, and hafnium. These forms a L1 to L3ZR type precipitates. You can see it, and it is governed to a novel two-stage heat treatment process where the coupling of copper rich and L12 precipitate takes place. Okay, so here you can see that in the microstructure, the bright plates corresponds to the copper rich and the round precipitates corresponds to L3ZR. If you see the hardness curve, presence of zirconium and tantalum, you can see that the hardness doesn't drop, while without zirconium tantalum, the hardness drops drastically. So this is a Hadoff image where you can see that the atomic number contrast, as I told you, and you can see that these L12 has a zirconium. That's why it's a high atomic number, so you will get a higher contrast, and these are coherent with the aluminum and also the plate precipitates. This is a three-dimensional view of this particular alloy, where you can see that the red color corresponds to the Al3ZR, while the plate corresponds to the copper, which are actually touching each other. So means these are heterogeneously nucleated on the copper-rich precipitates are heterogeneously nucleated on the prior present Al3ZR precipitates. If you see the interfaces, the coherent interface, you can see there is an enrichment of zirconium at the copper-rich at the interface of the copper precipitate and the alpha matrix. This shows that the diffusivity of copper is hindered by the zirconium segregation. Also at the incoherent interface, you see this uh, bright color atomic columns. These corresponds to the presence of hafnium and tantalum. That also restricts the growth of the by the ledge mechanism of these precipitates, and this have a direct consequence on the high temperature properties, where the high temperature strength can go up to 250 MPa, while for the 2219 T8 temper it is around almost 150 MPa, 150 to 160 MPa at 250 degrees Celsius. So this is how, in correlation with the microscopy and also the tomography, we can get the actual reason for the high temperature properties. This is another example of an interfacial segregation of an aluminum nickel alloy. Usually aluminum silicon cast alloys are used for the piston applications in automobiles, but nowadays the temperature, because of the fuel efficiency, to increase the fuel efficiency, the temperature capability also should increase. So what they are doing is they want aluminum silicon alloy, they cannot sustain beyond 200 degrees Celsius. So we are looking at, so these are the researchers are looking for an alternative to the aluminum silicon eutectic alloys. Here there is a class of alloys which are aluminum nickel based. Here it forms a eutectic from an alpha aluminum and Al3Ni. But these have a very low ductility and low strength, even though they are stable at high temperatures. To improve the strength, what we did is we added a zirconium of 0.15 to this eutectic structure, and you can see that this zirconium addition leads to the very fine precipitates inside the alpha aluminum. We made the atom probe needle where we have covered both Al3 Ni and the matrix, and you can see that there is a homogeneous distribution of Al3 zeta precipitates inside the alpha matrix, and also there is a presence of Al3Ni. If you take the composition profile across the Al3Ni, you can see there is a significant segregation of zirconium. Okay, and this segregation of zirconium stabilizes the interface of alpha aluminum Al3, lowers the interfacial energy and stabilizes it at high temperature, so that you can get a very high temperature stable and very high yield strength at room temperature, that is and also higher yield strength than the binary alloy at 250 degrees Celsius, around 200 MPa. Okay, these exceptional mechanical properties are related to the interfacial segregation of zirconium at the interface. I will give you another example of a grain boundary. This is related to the grain. This is related to the segregation this is related to the compositional partitioning across the reaction front. So when any alloy is cold worked and recrystallized, there is a recrystallization process occurs by the movement of the grain boundary. And if this is a multi-component alloy, there must be a solute transport mechanism across the reaction front, which governs the which actually controls the driving force for this particular movement. So my student Nitin, what he did is he has taken a multi-component alloy with aluminum content, nickel, cobalt, chromium, aluminum, where aluminum is a tendency to form L12 precipitates with the nickel, cobalt, chromium matrix. Okay, so this is they form a lamellar structure. So lamellar structure is due to the movement of the grain boundary, and it happens due to the discontinuous precipitation while during the movement of the grain boundary. And there is also a non-recrystallized grains. So this recrystallized grain, this grain boundary moves further so that this lamellar structure develops while movement. Okay, so this is a typically discontinuous precipitation. And he has identified a reaction front where this reaction front goes further, and it forms a compositional precipitation of the gamma prime precipitates behind the reaction front. So he has taken a lamella from this reaction zone. You can see this is a reaction zone, and what is and he has prepared the sample by in-plane lift out by these regions, okay, on the Molly grid. And here he is showing a bright field and a dark field image from the reaction front. And here you can see that the bright field image contains A grain and B grain. And if you orient the A grain to a zone axis, you can see that the B grain is out of zone axis. It shows that actually we have captured the reaction front with different zone axis value. Okay. Now in the A grain, if you take the diffraction pattern, you can see there is an appearance of L12 spots. Similarly, for the grain at the C, you can see that the appearance of L12 spots. It is at the different orientation. He has taken the dark field from these aluminum spot to just make differentiate between the non-recrystallized grain and the recrystallized grain. Interestingly, at this location where there is a dark region, if you take the diffraction pattern, there is no superlattice spot. It means that there is a precipitate free buffer zone which is formed just near to the reaction front. If you take a bright field image which is out of zone, you can see that there is a reaction front, there is a precipitate free buffer zone, and between the precipitate free buffer zone and the non-recrystallized grain, there is a boundary which is called PFG boundary. Same atom probe needle was field evaporated, and as expected, you can see that at the region C, there is a discontinued precipitates of L12 ordered. In a non-recrystallized grains also, because of the aging, you can see that the spherical precipitates appears, but between these two, there is an appearance of a precipitate free zone ahead of the reaction front. Now you have a three-dimensional composition profile. If you see the profile across the reaction front in the gamma prime, there is a nickel enrichment. However, if you see the boundary between the PFG and the non-recrystallized grain, you can see that there is a change in composition. If you do the top section or then you can see there is a chromium enrichment, and in between the chromium enrichment, you can clearly see that there is a dissolution of precipitates is happening. This dissolution of precipitates is happening exactly at that particular plane. And if you take the composition profile, we see that exactly similar to the nickel, there is a nickel segregation. And along the chromium rich part, you see there is an enrichment of chromium, while depletion of nickel and cobalt and aluminum are almost same. Okay, based these composition profiles, he has also taken the composition profile along in perpendicular to the reaction front. You can see there is an increment in the nickel and there is a decrease in the chromium. So based on the composition profiles, what we did is that there is a local solute diffusion mechanism which is happening, and the main controlling factor is the diffusivity of the nickel, because of which there is a formation of a precipitate free buffer zone, and the thickness of the zone depends upon the interdiffusivity of these solutes across the boundary. Okay, so here the nickel diffusivity plays a very important role during recrystallization of this particular alloy. So this was revealed by the combined usage of microscopy and tomography. Another example, as an interesting example, is from the Tata Steel, where they have provided a ferritic steel which are very prone to the hydrogen embrittlement, and in this ferritic steel they can induce the carbide precipitation. And it was shown that in the literature that the carbides are prone to the trapping sites of for the hydrogen or the deuterium, but they don't know that hydrogen or deuterium is trapped at the carbides or at the interface. So they have given this sample. These are the precipitates which are present. This is the dark field image of, and you can see that the appearance of these precipitates, and this particular sample is charged chemically by the D2SO4 deuterium charging, where the deuterium diffuses to the matrix, and due to the presence of ferrite and precipitates, actually wherever the precipitates are present, which are niobium carbide precipitates, actually deuterium is partitioning to those precipitate inside the unit cell. Okay, so this is how they have identified that niobium carbides are the effective for the trapping of deuterium, and based on this they can actually improve the processing such that these precipitates volume fraction increases, or so that they can trap more and more deuterium, so that they can prevent or they can increase the resistance towards the hydrogen embrittlement effect. Okay, with this, what I have shown till now is the several examples related to the defects, grain boundaries during recrystallization, and also the deuterium trapping or the hydrogen trapping on the precipitates. And these are not only to the related to the structural materials. These also, the microstructural features are also responsible for the properties of magnetic alloys, bond coats, aluminum based alloys. Okay, even in the functional materials. So the interfaces plays a very crucial role, and the structure and the chemistry. So with this, what we get to know is the structure and chemistry is interrelated. Depending upon the local structure, the composition may change, and the diffusivity of those solutes are the rate limiting solutes which governs the overall properties of the alloy. Okay, so with this, I will end this class now. Okay, and I hope that you got a good picture of how to use this electron microscopy and the tomography for this for the analysis. Thank you very much.